Oh, welcome to the problem type problems from class 27, physics 200, year in the year of the COVID virus. Um, so, what we have is these kind of equations for which the most critical ones are the ones that deal with the induction, right? So this is kind of the main event, and in order to get the direction of this EMF, we had a couple of ways of doing it, and I don't know. I would say by far the easiest way was by this Lenz's law approach, where we say that the induced current is going to fight the change in the magnetic field. And let's take a look at some problem type problems. Okay, so here's a somewhat complicated circuit, and let's start with B as opposed with A. I don't know why I want to do it this way, but I do. So the context for B and C, both of them, is that this switch is closed, right? So what we have is current that's flowing from the positive end of this battery. And what that means, if you apply the right-hand rule to any one of these turns, put your thumb in the direction of the current, inside the coil, your fingers would be pointing that way. So that's the direction of the magnetic field inside the coil. And we're going to bring the B coil closer, which means that it's going to experience a bigger field, right? When it was way out here, it only experienced that, and now that it's closer, it's experiencing that. So these induced currents are going to fight that change, right? So what they're going to try and do is make their own magnetic field, which tries to kill the change that occurred. Won't succeed. So if we know that the magnetic field inside of this coil is this way, what way does the current have to flow in order to make that magnetic field? And if you think about it, ooh, I hate that I keep hitting that. What's required is to make a current that is going like that, right? So when you move it closer, the induced current is going to be going from B to A this way. Okay, so the part C is similar. I guess I would say very similar. So let's kind of erase all the stuff that we said. So what's happening is the magnetic field, right, which we said is initially going like this. If I reduce this resistance, smaller number in the denominator means that there's going to be more current. So the magnetic field is going to be bigger in the future. And so the induced current is going to try and fight the change. It's going to try and make its own magnetic field, which knocks it down to what it was in the beginning. So in order for the current in B to make a magnetic field that's to the left, what has to happen is that the current needs to be going like that. And you can check that out by putting your thumb in the direction of one of those little arrows for the coil, for this particular arrow, for example, and then inside the coil, your fingers would be pointing towards the left. Okay, so finally back to A. So the magnetic field has been on for a while, and so there is a magnetic field that is this blue arrow, right, this guy here. And now we're going to open the switch. So if we open that switch, the current is going to relatively quickly go to zero. So the magnetic field in the future is going to be smaller. And what the solenoid will do is it'll try and maintain that magnetic field by making its own magnetic field fighting the change, right? The change was to get smaller, so it's going to try and maintain that. And if you think about which way that means the current has to flow, it has to flow around like that. And again, if you're not sure about that, if we take a look at this arrow, put your thumb in that direction, it's going to make a magnetic field that is to the right. Okay, so here we've got a circuit, and what we have is initially this thing is, the switch is open the way it is shown, and what's going to happen is we're going to close the switch, we're going to make the connection, and suddenly we're going to have a current that is flowing around this way, right? This is the positive end, and that's the negative end of that battery. And those guys by themselves, if you put your thumb in the direction of those currents, it's going to make a magnetic field inside this loop that is out of the page. And that inner coil doesn't like that, right? It's going to try and fight the change. It's going to try and make its own magnetic field that is going into the page. And it would do that by having a current that is going around like this, right? Okay, so if the switch has been closed for a long time, the current has reached some steady value. Typically it would reach that in a very short period of time. So if the current is constant, that means that the magnetic field is a constant that it's producing, and that means that the change in the magnetic field is zero. So there's no change in flux, and so there's no EMF. So there's going to be no current that's going. Okay, so for part C, the current, the switch was closed, so there was a current flowing around like this. So there was a magnetic field that was going up, but now this switch is opened, and so that current is going to very quickly decline. So the magnetic field was out of the page and big, but in the future it's going to be zero. So the inner loop doesn't like that. It wants to make a magnetic field that would try and fight that change. It wants to make its own magnetic field now that is up. And so it would have the current going around that way. Okay, so here we have kind of a more numerical problem. We are told the radius, and from that we can get the area of this loop, and we're told the resistance of this loop, and we're told that the magnetic field was pretty big. 8 teslas is pretty big, but it's getting smaller. And in the end, what I guess this is a somewhat disguised question. We're going to need to find the current that is flowing in this loop, because the electrical energy that's dissipated is I squared R. Okay, so of course the current is going to be determined by the EMF divided by the resistance, and they've told us what the resistance is, so it's a matter of calculating the EMF. And the EMF is going to be minus, we've got one loop, the area times the change in the magnetic field. Now, all this sign is doing is telling us the direction of the current flow. So let's do that guy first. So the magnetic field is pointing out of the page, and it is getting smaller. The induced current is not going to like it. It's going to want to fight the downward change by making its own magnetic field that is also out of the page. And it would do that by making a current that's going around like this. So that's the direction of the current flow. The magnitude of the current flow, we need to get this voltage. And the area is, of course, pi times 0.048 squared, and the time rate of change in the magnetic field is 0.68 Teslas per second. Notice I've dropped all of the signs. All of those signs are just what's involved in getting this direction. Okay, so this is a plug and chug. So we've got pi times 0.048 squared times the time rate of change in the magnetic field, which is 0.68 Teslas per second. So we've got a voltage that is basically 5 millivolts. 4.92, I guess, if we insist. So the corresponding current is going to be that voltage divided by the corresponding resistance, which is 0.16. So what we want is that voltage divided by 0.16. So the current is going to be basically 30 milliamps. And what we want then for the power is I squared R. So that's the previous result for the current squared times 0.16. So 1.51 times 10 to the minus 4th watts. Okay, so then finally a motional EMF problem. Again, kind of a numerical value. So we've said that the EMF that is generated is the length of the piece, the velocity, times the magnetic field. And all of this thing is just giving us the time rate of change in the flux for the whole circuit. But we can calculate it. The length of this segment here we're talking about is 0.5. The velocity is 7.5 meters a second. And the magnetic field is 0.8 Tesla. So 0.5 times 7.5 times 0.8. 3 volts even. Okay, let's lose track. So here we've got the magnitude of the EMF. What direction is the current flow going to be in the wire. So it's easiest to think about positive charges. So if we're thinking about positive charges, they are moving with a velocity this way. The magnetic field is into the page, so if I cross this V into that, I get a force on those charges that is going up. So that's the way the conventional current is going to flow. So now we're supposed to think about what the current is. So the current is the voltage divided by the resistance, and I can do that in my head, right? 3 divided by 1.5 is 2 amps. So if we have a current that is 2 amps, so remember the equation for the force, right? The force is going to be the current times the length crossed into the magnetic field. So if I cross that current into the magnetic field, I get a force that is this way. And the magnitude of that force, right, is going to be the current, which is 2 amps, the length, which is 0.5, and the magnetic field, which is 0.8. And I don't know, we can do this in our head. 2 times a half is 1, so this is 0.8 newtons. And of course, that's the magnetic force. In order to keep this thing moving, we're going to have to fight at a constant velocity, right, which means no net force. I have to push it to the right with that force. So rate of work, power, is the force times the velocity. So I've got my 0.8 newtons times my 7.5 meters a second. So I'll probably do that one in my head too. Let me rearrange this thing so that it fits a little bit better. So 0.8 times 7.5, 6 watts even. So I'm doing 6 watts of work. How much electrical work is doing? So presumably energy should be conserved. So what we've got for the electrical energy is I squared R, and we know that there are 2 amps, and we know that the resistance is 1.5 ohms. So we've got 4 times 1.5, which I can do in my head, is 6 watts. So conservation of energy is looking good. Okay, so that's the end of the problem type problems in something like the right amount of class time. These directions are tricky, and we'll go over the iQuiz questions next time, and so I hope you'll think about them yourself so that you can be challenged by the hopefully correct answer that I'll give. Okay, so that's it.